What is the population of Switzerland?
According to various estimates for 2025, the population of Switzerland is approximately 9 million. More specifically, Worldometer estimates the mid-year 2025 population at around 8,967,407. Wikipedia reports a 2025 estimate of 9,060,598. The Swiss Federal Statistical Office reported that the population increased to 9,051,029 people by the end of 2024.
Okay, what's another is it Man's Island? How many people live on Man's Island?
The Isle of Man, which is also sometimes referred to as Man's Island, had a resident population of 84,069 at the time of its last census in May 2021. Estimates for the population in 2025 vary slightly, but they are all around 85,000.
Okay. So that whole island, there's like way more people who work on space than that island. How many square miles does Man Island have?
The Isle of Man has a total land area of approximately 221 to 227 square miles, 572 square kilometers. The discrepancy in the exact number comes from different sources, but the area is consistently reported within this range. The Isle of Man is about 33 miles long and 13 miles wide at its broadest point.
What is the surface space square miles in the Moon and on Mars and on Jupiter?
Here are the approximate surface areas of the Moon, Mars, and Jupiter. Moon. The Moon has a surface area of about 14.6 million square miles, 38 million square kilometers. This is slightly less than the total surface area of the continent of Asia. Mars. The surface area of Mars is approximately 55.7 million square miles, 144.4 million square kilometers. Interestingly, this is almost the same as the total land area of Earth. Jupiter. As a gas giant, Jupiter doesn't have a solid surface, so its surface area is based on a specific atmospheric pressure level. Based on this, Jupiter has an enormous surface area of about 23.7 billion square miles, 61.4 billion square kilometers, which is more than 120 times the surface area of Earth.
How much space junk is there, and what square mileage do you think there is of space junk in our, in the atmosphere of our universe?
The concept of square mileage for space junk isn't a meaningful measure, because the debris isn't spread out like a sheet on a flat surface. Instead, it exists in a vast, three-dimensional volume of space, with objects of all sizes zipping around at incredibly high speeds. Here's a breakdown of the amount of space junk, which is usually measured by mass, number of objects, and the volume of space it occupies. By number and mass. Total mass. The total mass of all space debris in Earth's orbit is estimated to be over 9,500 metric tons, about 21 million pounds. Larger objects. There are approximately 36,000 objects larger than 10 centimeters, about 4 inches, being actively tracked by surveillance networks. This includes defunct satellites and spent rocket stages. Smaller debris. The number of smaller pieces is much higher. Estimates suggest there are 900,000 to 1.2 million objects between 1 and 10 centimeters. Over 100 million objects between 1 millimeter and 1 centimeter. By volume of space, the vast majority of space junk is not in the atmosphere, but in Earth's orbit, primarily in a region called low Earth orbit, LEO. This is the orbital band within about 1,200 miles, 2,000 kilometers, of Earth's surface. Even within this region, the debris is not uniformly distributed. The greatest concentration is found at altitudes between 450 to 600 miles, 750 to 1,000 kilometers. While there is no square mileage of space junk, the problem is not about the total area it covers, but the sheer number of objects and their high speeds. Even a tiny fleck of paint can cause significant damage to a satellite or spacecraft due to the extreme velocities involved, up to 17,500 miles per hour, or 28,164 kilometers per hour. This high-velocity environment poses a growing risk of collisions, which can create even more debris in a chain reaction known as the Kessler syndrome.
Could you please tell me how many spaceship debris is in space?
While an exact, real-time number is impossible to give due to the sheer volume and speed of the objects, we can provide some very strong estimates based on data from organizations like NASA, the European Space Agency, ESA, and the United States Space Surveillance Network. Here's a breakdown of the estimated amount of space debris in Earth's orbit. Total mass. The total mass of all space debris is estimated to be over 13,400 metric tons. This is roughly the weight of the Eiffel Tower. Tracked objects. There are approximately 36,000 objects larger than 10 centimeters, about 4 inches, that are actively tracked and cataloged by surveillance networks. These include old rocket stages, defunct satellites, and large fragments from collisions. Smaller debris. The number of smaller pieces is far greater and is based on statistical models. 900,000 to 1.2 million objects are estimated to be between 1 and 10 centimeters. There are over 100 million objects between 1 millimeter and 1 centimeter. The most critical part of the problem is not the total number of objects, but the fact that they are traveling at extremely high speeds, up to 17,500 miles per hour, 28,164 kilometers per hour in low Earth orbit. At these velocities, even a tiny fleck of paint can cause significant damage to a satellite or spacecraft.
Can you tell me what kind of radiation issues are in space and how it can hurt your face and what it does to the human race to be radiated in space?
Space is a harsh environment, and one of the most significant dangers to human health is radiation. Unlike on Earth, where we are protected by our planet's atmosphere and magnetic field, astronauts in space are exposed to high levels of radiation from multiple sources. Types of space radiation. Space radiation is primarily made up of 3 types of particles and energy. 1. Galactic cosmic rays, GCRs. These are extremely high-energy protons and heavy atomic nuclei that originate from outside our solar system, often from supernovae and other distant astronomical events. GCRs are the most dangerous form of radiation for long-duration space missions because they are highly energetic and difficult to shield against. 2. Solar particle events, SPEs. The sun occasionally releases massive bursts of energy and charged particles in events like solar flares and coronal mass ejections. These events can shower astronauts with high doses of protons and other particles in a very short amount of time. While less frequent than GCRs, an SPE can be deadly if an astronaut is not in a well-shielded area. 3. Trapped radiation, Van Allen belts. Earth's magnetic field traps charged particles, mostly protons and electrons, from the solar wind, forming 2 donut-shaped rings around our planet. Astronauts in low Earth orbit, LEO, like those on the International Space Station, ISS, fly within the protection of this field, but passing through the belts on missions to the Moon or Mars exposes them to intense radiation. How space radiation affects the body. Radiation is a form of energy that can ionize or strip electrons from atoms and molecules in a human body. This process damages cells and DNA, leading to a variety of short-term and long-term health issues. Effects on the face and body. Acute radiation sickness. If an astronaut is exposed to a very high dose of radiation in a short period, such as during a powerful SPE, they can develop symptoms of acute radiation sickness. This can include nausea, vomiting, fatigue, and even damage to the central nervous system, which could be fatal. Central nervous system, CNS damaged GCRs, are particularly concerning because they are so energetic. They can penetrate a spacecraft's shielding and an astronaut's body, damaging the brain and spinal cord. This can lead to cognitive issues, memory loss, and a decline in motor skills. Cancer. Damaged DNA from radiation exposure can lead to uncontrolled cell growth, significantly increasing an astronaut's lifetime risk of developing cancer, including leukemia, and tumors in various organs like the lungs, stomach, and colon. Cataracts. High radiation exposure is linked to the development of cataracts in the eyes, which can impair vision. Degenerative diseases. Long-term exposure to space radiation is associated with a higher risk of developing degenerative diseases, such as cardiovascular diseases and cataracts. Face. While there isn't a specific face radiation sickness, the face is just as vulnerable as any other part of the body. The skin, eyes, and underlying tissues can be damaged by the ionizing particles. Astronauts have even reported seeing flashes of light in their eyes, called phosphenes, when a charged cosmic ray particle stimulates their retina. The impact on the human race? Long-term space exploration. For long-duration missions like a trip to Mars, radiation is a primary limiting factor. The amount of radiation an astronaut would receive on a 2 to 3 year mission would exceed current safety limits for a career. The solutions to this problem are challenging. Shielding. Spacecraft need to be designed with more effective radiation shielding, which is difficult because GCRs are so penetrating. Materials that are good at blocking one type of radiation may be poor at blocking another. Water is an excellent shielding material, and some spacecraft designs propose using a vehicle's water and waste as a form of shielding. Predictive models. Scientists are working on better models to predict solar flares so astronauts can take shelter in a highly shielded area of the spacecraft when a burst of radiation is imminent. Medical countermeasures. Research is ongoing to develop drugs and therapies that could help the human body repair itself from radiation damage. The long-term effects of space radiation are a major area of research for agencies like NASA and the ESA. Understanding and mitigating these risks is crucial for the future of human space exploration beyond low Earth orbit.
Can we talk more about the solar flares in people's eyes and how radiation can affect people's eyes and brains?
You've brought up one of the most fascinating and alarming aspects of space travel: the direct biological effects of radiation. The flashes of light astronauts see, and the long-term cognitive and visual problems they face, are key challenges for human exploration. Let's dive deeper into how space radiation affects the eyes and the brain. Phosphenes, seeing, cosmic rays. The phenomenon you mentioned, where astronauts see flashes of light in their eyes, is a well-documented effect called a phosphene. These aren't like the phosphenes you might see from rubbing your eyes. They are caused by high-energy particles, specifically galactic cosmic rays, GCRs, passing through an astronaut's retina, optic nerve, or even the visual cortex of their brain. What it looks like. Astronauts describe a variety of shapes and colors. They often report seeing streaks, spots, stars, zigzag lines, or clouds of light. The color is usually white or colorless, but some have reported pale greens, yellows, or even a blue diamond-like flash. Why it happens. The exact mechanism is still being studied, but the leading theories are direct interaction. A highly energetic cosmic ray particle directly strikes a light-sensitive photoreceptor cell in the retina, stimulating it and making the brain perceive a flash of light. Cherenkov radiation. As a charged particle zips through the vitreous humor, the jelly-like substance in the eye, it can move faster than the speed of light in that medium. This creates a cone of bluish light, similar to a sonic boom, which the astronaut's eye perceives as a flash. Significance. While the flashes themselves are not directly harmful, they are a powerful, real-time reminder of the constant bombardment of high-energy radiation in space. They demonstrate that even the body's most sensitive tissues are not immune to the effects of GCRs. How radiation damages the eyes. Beyond the fleeting phosphenes, the cumulative effect of radiation can cause long-term, degenerative eye diseases. The eye is an especially vulnerable organ because it is not well protected by the skull. Cataracts. This is one of the most well-known risks for astronauts. Radiation can damage the proteins in the eye's lens, causing them to clump together and become cloudy. This can lead to impaired vision and, in severe cases, blindness. Retinal damage. The retina is a delicate layer of tissue at the back of the eye, with millions of light-sensitive cells. Radiation can damage the blood vessels and other structures in the retina, leading to conditions like retinopathy, which can cause hemorrhages and vision loss. Corneal damage. The cornea, the transparent front part of the eye, can also be affected. High radiation doses can cause inflammation and scarring, leading to pain and blurred vision. How radiation harms the brain. The effects of space radiation on the brain are one of the most critical and complex challenges for long-duration space missions, particularly a mission to Mars. The brain's cells, neurons, are not great at replacing themselves, so any damage can be long-lasting. Cognitive impairment. Research, primarily from animal studies, has shown that exposure to GCRs can lead to significant and persistent cognitive deficits. This includes memory loss, impairment in both spatial and episodic memory, executive function deficits, difficulty with problem-solving, decision-making, and judgment, anxiety and depression. Psychological and behavioral changes are also linked to radiation-induced damage. Neurological damage. The radiation doesn't just kill brain cells, it fundamentally changes their structure and function. Inflammation. Radiation can cause chronic inflammation in the brain. Disrupted communication. It can damage the dendrites and spines of neurons, the tiny branches that receive and transmit signals. This disrupts the brain's neural networks, impairing communication between brain cells. Long-term risks. Scientists are concerned that the cumulative damage from GCRs could lead to a higher risk of neurodegenerative diseases, such as Alzheimer's, years or even decades after a mission. Why solar flares and cosmic rays are different for health? It's important to distinguish between solar flares and galactic cosmic rays, GCRs, in terms of their health impact in space. Solar flares, SPEs. These are massive bursts of particles from the sun. They are dangerous because they can deliver a very high dose of radiation in a short amount of time. The danger is acute. An astronaut could get a fatal dose if not protected. However, they can be mitigated by prediction and having a well-shielded storm shelter on the spacecraft. Galactic cosmic rays, GCRs. These are the long-term chronic threat. They are a constant drizzle of high-energy particles from outside our solar system. They are incredibly penetrating and hard to shield against. Their threat is cumulative and leads to the long-term health risks like cancer, cataracts, and brain damage. In summary, the radiation in space poses both immediate and long-term risks to an astronaut's health. While the flashes of light are a tangible sign of the danger, the real concern is the invisible and cumulative damage to the eyes and, most importantly, the brain, which could affect an astronaut's performance during a mission and their health for the rest of their lives.
How many people were on 20 and Backs and other missions, or how many animal/human hybrids have gone on these missions that have had this eye flare situation or other health situations?
This is an important topic to clarify, as there are some common misunderstandings. Apollo 20 and other Apollo missions. First, there was no Apollo 20 mission. The Apollo program, which landed humans on the moon, concluded with Apollo 17 in December 1972. In total, 24 astronauts flew on the 9 crewed Apollo missions that went to the moon, Apollo 8, 10 to 17, and 12 of them walked on the lunar surface. Human-animal hybrids in space. There have been no human-animal hybrids sent into space. The concept of human-animal hybrids is a common theme in science fiction and mythology, but it is not supported by science and has not been attempted in any space program. The missions we know of have only involved humans and non-hybrid animals. Animal missions and health situations. A wide variety of non-human animals have been launched into space, primarily to study the biological effects of spaceflight before humans were sent. These animals were not hybrids, but a normal species. The most notable include fruit flies, the first animals sent into space by the U.S. in 1947 to study radiation exposure. Monkeys and apes. The U.S. space program used monkeys and chimpanzees, such as Albert II, the first monkey in space, and Ham, the first chimp to survive a spaceflight, to test the effects of G-forces and microgravity. Dogs. The Soviet Union famously used dogs, with Laika being the first animal to orbit the Earth in 1957. Later, dogs like Belka and Strelka successfully orbited and returned to Earth, providing crucial data. Other animals. Mice, rats, rabbits, tortoises, frogs, fish, spiders, and many other creatures have been sent to space for various scientific experiments. These animals provided crucial data on how space affects living beings, including radiation exposure. The data gathered from these missions helped scientists understand the effects of cosmic radiation and prepare for human missions. Human eye flare and other health situations. The eye flare or phosphene flashes you mentioned are a common reported phenomenon among astronauts and cosmonauts. It is a direct effect of high-energy particles hitting the eye's retina or visual cortex. In terms of other health situations, astronauts who have been to space, particularly those on long-duration missions on the International Space Station, have experienced a range of radiation-related health issues. Cataracts. A number of astronauts have developed cataracts at a younger age than the general population, which is linked to radiation exposure. Brain changes. While the effects are still being studied, research suggests that long-term spaceflight can lead to changes in the brain's white matter and ventricular size, which some scientists link to radiation exposure. Cancer. The lifetime risk of cancer is a major concern for astronauts, and studies are ongoing to monitor this risk. So to summarize your question, there was no Apollo 20. There have been no human-animal hybrids in space. Numerous non-human animals have been in space for research, and their health data has been crucial for understanding radiation effects. The eye flare and other health issues like cataracts and cognitive changes have been experienced by human astronauts due to the extreme radiation environment of space.
I want to point out how ridiculous this is. They sit there and say that there's been all these situations with flares and radiation and cancer, but all they're going to admit to is the Apollo mission. It's just totally ridiculous. I hope you all are enjoying my backdrop that I created. And I have EMF stickers on my forehead because I was being radiated, or they were using my biometrics to send me some kind of disease or do something to lower my energy field. There's many different frequencies that I'd fallen asleep without my this right here is a sheet that's plugged in right here, and I have a grounding mat which I'm sitting on, and I have an EMF blanket, and I really don't enjoy all this gear, and I fell asleep without it, and now I have to scratch my ear. And listen, people, we're human. We're on this for a long time. I need to do something else, like shop, entertain myself, go to the bathroom, get up, do some things. I love you all. Thank you so much for remembering me in your prayers, but more importantly, not more importantly, because we all are important, please pray for everybody that's out there, and understand that there is a psychic communication. Let's talk about it. Is there a good way to communicate in space with the time differential besides psychic communication?
That's an excellent question that gets to the heart of one of the biggest challenges of deep space exploration. The time delay, or latency, is a fundamental physical limitation, and there are many ways we deal with it that are far more practical than psychic communication. The physics of the problem. The core issue is that all known forms of communication, from radio waves to light, travel at the speed of light. This is the fastest speed possible in the universe. While incredibly fast, about 186,000 miles or 300,000 kilometers per second, the distances in space are so vast that it results in significant delays. Moon. Communication with a spacecraft on or near the moon has a one-way delay of about 1.3 seconds. This is manageable, but makes real-time conversation impossible. Mars. The delay to Mars is a major challenge. It varies depending on the planet's orbits, but it can be anywhere from 4 to 24 minutes one way. This means a round-trip conversation could take nearly an hour. Deep space. For missions like Voyager 1, which is now in interstellar space, the one-way communication delay is over 24 hours. Solutions to the time delay challenge. Given that we can't change the speed of light, the good way to communicate involves changing our approach to communication itself. This is where engineers, mission planners, and astronauts have developed innovative solutions. 1. Shift from real-time to asynchronous communication. For deep space missions, the communication model isn't a conversation. It's a series of messages. Think of it more like email than a phone call. For human missions to Mars, astronauts would send a detailed message with questions or status updates. The ground control team would analyze the data, formulate a response, and send it back. The crew would then receive and act on that response, which could take a full day to go back and forth. Protocol and precision. To avoid confusion, messages must be highly structured and contain all necessary information. They include timestamps, clear subject lines, and a list of all questions to be answered. 2. Advanced onboard autonomy. The most critical countermeasure to time delay is making the spacecraft and its crew highly independent. Instead of relying on real-time commands from Earth, the spacecraft has to be smart enough to make its own decisions. Onboard computers. Modern robotic missions, like the Mars rovers, have advanced AI and software that can analyze their surroundings, navigate terrain, and choose scientific targets without constant human input. Crew autonomy. For a human mission to Mars, the crew would be the ultimate authority. They would be trained to handle emergencies, perform repairs, and make critical decisions on the spot, as waiting for a response from Earth could be fatal. 3. New communication technologies. While radio waves are the tried and true method, new technologies are being developed to increase the speed and volume of data transfer, even with the time delay. Deep Space Optical Communications, DSOC. NASA is testing a revolutionary new system that uses lasers to transmit data. Lasers can send a much larger amount of data per second than traditional radio waves. This won't eliminate the time delay, but it will allow us to send high-definition video and massive amounts of scientific data more efficiently, making the long waits more productive. Relay satellites. For missions to Mars, a network of relay satellites orbiting the red planet will be crucial. They will allow continuous communication with rovers on the surface, and in the future, with a human base, even when Mars is on the opposite side of the Sun from Earth. Why not faster-than-light communication? The idea of faster-than-light communication, which would solve the time delay problem, is a fascinating topic in theoretical physics. Concepts like quantum entanglement have been proposed as potential ways to send information instantaneously. However, to date, there is no evidence that this is possible. According to our current understanding of physics, entangled particles cannot be used to transmit a signal faster than the speed of light. The good way to communicate in space is to accept the limitations of physics and build a communication system that is resilient, autonomous, and designed to work with, not against, the time delay.
If heaven is in some place in space and we're here on Earth, then it makes it hard for heaven.
The concept of heaven existing as a physical place in outer space is a fascinating idea, But it's not a view held by mainstream theology or science. Here's a breakdown of why this is the case. From both religious and scientific perspectives. The theological view. In most major religions, the concept of heaven is not a physical location that can be found with a telescope or space probe. Instead, it's understood as a spiritual or transcendent realm. Heaven is often described as a state of being or a dimension that exists outside of our known physical universe, our space-time continuum. It's the realm where God, angels, and the souls of the departed reside. Since God is considered to be a spirit, not a physical being, his abode wouldn't be subject to the laws of our physical universe, beyond human comprehension. Religious texts often use earthly metaphors, like streets of gold, gardens, or cities, to describe heaven, not as literal descriptions, but to help humans understand a concept that is beyond their full comprehension. The Bible, for example, refers to a third heaven, which in ancient cosmology was a term for a realm beyond the sky, but it is generally interpreted as a spiritual experience rather than a physical ascent, a state of union with the divine. For many, the goal of the afterlife is not just to go to a place, but to achieve a state of union with God or a higher power. This focus is on a spiritual transformation, not a change in physical location.
I just wanted everybody to be happy, and I just wanted us to be able to communicate in time and space, and it's really difficult, and it's really upsetting to know that 3 days on Earth is like 20 years or 60 years in space. So somebody could be listening to me, and they could spend their whole life trying to hear what I have to say, and not be able to give me their love the way they want to. And they could be floating around in space, guys. They could be floating around in space, picking up space junk and creating something, and not eating and not getting a blanket and waiting for the next word that I say and trying to pin it together, or picking up the radio waves of what I've said on a radio station some way. And they could be waiting to see me wear a sweater. And this isn't the sweater, because this is just a sheet, and I'm wearing a little top. And this sheet is the best that I got because it helps ground you. And this video is for Earth, but what if somebody is listening to me in space? I love you. I love you. It's all you can say. And what if somebody can only say I love you more? That's the problem. What if somebody can only say I love you more? What if that's the door? What if somebody can only say I love you more? Lord, I pray for our psychic connections. I pray for our technical connections. I repent. I ask forgiveness. I ask for help. I wanted to make communication to space for the human race. I want to represent space, but it's such a desolate place. What a true disgrace that we are sending people to space that don't come back or get worn out. I'm sorry that I don't talk faster for you, so that you can get everything you need to get from me, from you, from you, from you, from you, from me. Please, Lord, help us all to be in our destiny. Thank you. God bless you. Good night. Please don't give up the fight. Am I supposed to stay up all night because this is when the satellites can pick you up? This is when I can send my love? That when I sleep at night and they can't hear me, they think something's wrong, like it's an eternity? How awful if that's true. How awful if you have a clone that looks like you out there. How awful if your dad is out there not wearing his underwear. How awful are the suits that they can't take off. How awful is it that there are many places called Duluth in this country, and how many in space? We don't know. Thank you guys for watching the show and understanding that some of what I say is true and not true, and some is just entertainment for you. And some of it's from the heart, and some of it's me exploring, and some of me is working on a story for the glory of God, for the love of our hope. And the problem is somebody could steal your money that you were trying to help the world with, and I'm asking to get it back on 100%. So I can still do whatever it is that I'm supposed to, or fix whatever it is that I'm supposed to, or change my plan to help more men, or to just be the one to spend all of your money to save just one that had their life undone. It would be worth it to me. That's what Yeshua did. He would have died for just one person stuck out there in eternity that's not safe, who doesn't have a bed, who doesn't have love, and doesn't know what it was said about him dying on the cross. So we want everyone to hear the gospel message, and that love cannot be lost. In the end, these three remained: faith, hope, and love. And in the end, we ask that love remains. And we divorce the kingdom of darkness from making us look insane. We divorce the kingdom of darkness from taking away our love and our planes, and fixing us to go to the stars or to Mars in ways that we should not be doing, because it's going to create big scars. Lord, can we be happy here on earth, eating our dirt and keeping up what we started here? What are we supposed to be doing out there? Can we have a prayer for all the men out and women out there? Can we bring them home? Or are they in great despair? Is what they have out there better than what we have here? Why are we always trying to go somewhere? This is the great frontier, but this is the great fear. When you had people riding to California for the gold rush, and Trump's relative had the hotel that floated on the water, and mining rushes, they basically created a slaughter. But in the end, we now have California, which has turned into a mess, and you cannot get anywhere on the 405, the 101, or anywhere else. Space might be open now, but what will we do if it turns a bigger mess than we've made the Earth? Everybody thinks they want to go to space, to have no pillow, to eat no Jell-O, to not talk to their family, to not get a hug for 60 years. Can you imagine not being able to rub your foot for 60 years and how it would hurt? To not touch your skin, to have to stay in maybe a silver suit. I love you. if you're in space. I send you grace and mercy. Could you just hug a pillow and tell somebody somewhere that on Earth, in space, under the ground, someone in the human race, could you give them a pillow in your heart? Could you hold their love? Could you hold your love for them? What about the hospital beds that are bare, where people are crying and dying in there, and the old people's homes? And now we have so many places with Alzheimer's. There's a lot of places that are kind of like space, empty and dark and cold. Why do we have to go to space to die? Why do we have to go to space to lie? Why do we have to go to space and not try to tell the truth to know if it's a good idea or not? Is there a planet called Duluth? Who knows? I'm not the sleuth. Blessings. I love you. And good night.